At the outset of World War II, German armored forces relied on machines designed for speed and coordination. Early panzers were relatively light, simple to produce, and intended to enable rapid maneuver, the core of Blitzkrieg tactics. Their value lay not in raw mass or heavy armor, but in mobility, to break through, encircle, and exploit weaknesses before the enemy could react. That paradigm began to shift as German forces encountered new and more capable enemy tanks. In Western Europe, and later on the Eastern Front, opposing designs demonstrated that mobility alone was insufficient. Tanks with thicker armor and more powerful guns could survive hits that earlier German vehicles could not. Confronted by this technical reality, German planners and engineers faced a stark choice: improve protection and firepower, or accept rising battlefield losses. The enemy that most dramatically altered German priorities was the Soviet T34. Introduced in 1941, the T34 combined sloped armor, a robust 76mm gun, and wide tracks that improved cross-country mobility. Its design offered a balance of protection, firepower, and production that confounded German expectations. Where earlier German guns often failed to penetrate enemy armor, the T34 could both absorb and deliver decisive blows. The appearance of this tank forced German designers to reconsider the size and capability of their next generation of armored vehicles. Out of that pressure arose a new generation of German tanks. The Panzer V, known as the Panther, was conceived specifically to regain parity with the T34. It featured sloped frontal armor and a high-velocity 75mm gun. In combat, the Panther generally outclassed older German types and performed well against many Soviet tanks. But these improvements entailed a substantial increase in mass. A larger gun required a more massive turret and mounting. Thicker, more effective armor required more steel and a stronger hull. The Panther's performance came at the cost of greater weight. And with that weight came new engineering challenges. Parallel to the Panther program, Germany produced even heavier machines, the Tiger series. The Tiger one carried the legendary 88mm gun and heavy frontal armor that could defeat most Allied tanks at long range. Its successor, the Tiger II, or King Tiger, pushed those parameters further, combining very thick armor with a long, high-velocity gun. These vehicles offered unmatched firepower in single engagements, yet their sheer mass, often well over 50 tons for the Tiger one and approaching 70 tons for later models, created profound operational drawbacks. Heavier tanks strained engines, transmissions, and suspensions. They were more likely to suffer mechanical failures, especially when rushed into production or operated in harsh conditions. Movement across soft ground, bridges, and narrow roads became more complicated and time-consuming. Fuel consumption climbed, placing additional burdens on logistic networks already under stress. In short, while heavy tanks could dominate localized encounters, they increasingly relied on robust supply, maintenance, and transport infrastructure to be effective. Political and strategic decisions amplified these technical trends. Adolf Hitler took a personal interest in weapon development and often demanded more armor or more powerful armament late in projects. Such interventions sometimes compounded weight increases and delayed production. Moreover, Germany's industrial capacity differed sharply from that of its principal opponents. Whereas the United States and the Soviet Union emphasized mass production of reliable medium tanks, the Sherman and the T-34, respectively, Germany invested substantial resources in producing relatively small numbers of complex, heavy vehicles. This contrast in approach had strategic consequences. The Allies could absorb losses and replace tanks quickly. Germany's heavier, more capable tanks were impressive in combat, but they could not be fielded in the numbers needed for sustained, large-scale operations. The result was a recurring trade-off. A technologically superior tank could win an engagement, but the inability to replace losses or maintain numbers over time undercut strategic effectiveness. Manufacturing realities and the escalating arms race also played a role. Improvements in enemy guns prompted increases in armor. Increases in armor prompted larger guns to penetrate them. This spiral pushed design toward greater size and weight. At the same time, Allied strategic bombing and resource shortages made production and repair more difficult, magnifying the shortcomings of complex heavy design. By the late stages of the war, the consequences of this trajectory were visible. Breakdowns and logistical bottlenecks reduced the operational availability of many heavy German tanks. Crews faced maintenance challenges, and commanders had to plan around the limits imposed by weight and supply. In battlefield terms, technical superiority did not always translate into decisive advantage when mobility, fuel, repair, and numbers were decisive factors. The story of German tanks growing heavier during World War II is thus a study in trade-offs. Designers sought to counter new threats with improved firepower and protection. Political priorities and the desire for qualitative superiority encouraged increasingly massive machines. But those gains in armor and armament imposed costs in production, mobility, reliability, and logistics. In an industrial war where quantity, sustainment, and flexibility mattered as much as battlefield performance, those costs proved decisive. In the end, the heavy tanks remained striking symbols of technological ambition and wartime urgency. They illustrate a fundamental lesson of armored warfare. Effectiveness is not only about the strength of individual machines, but about the system that supports them. Factories, fuel, spare parts, roads, and the ability to put machines on the battlefield when and where they are needed. The history of German armored development in World War II therefore reflects a larger truth. In modern war, operational and industrial realities shape and often limit technological aspiration.